In the last video, we installed Pybricks firmware on a Spy app and learned how to use the drive-based class. Today, we build on that. We're going to make our robot drive in a perfect straight line using a PID controller built step by step. But first of all, let's talk about with what we will use PID. The Spike Prime app has a built-in gyroscope, IMU. Pybricks let us read the yaw angle, how many degrees the robot has rotated from its starting position, and we can ask it how many degrees have I turned since we started. With this code, where in the beginning we should reset our heading to 0, and then with this loop we can ask the exact angle of the robot. Let's simply talk about what the PID controller is. Look at this graph. The straight horizontal line is our target, 0 degrees, perfectly straight. And the red line is what actually happens when the robot drives. Right here at the start, the robot drifts a lot to the left. Big drifts, so the controller sends a big correction and the line comes back down fast. Now here the robot is only little off. Small drift, small correction, and you can see the line barely moves. And right after it will happen again and again until the robot will be aligned with the line perfectly. And the PID controller stands for proportional, integral, and derivative controller, where proportional part reacts to the current error, and integral part reacts to the error that builds up over time, and derivative part reacts how fast the error is changing. Let's start with the simplest version, just the P term. Proportional. The idea is simple. Error equal to target heading of your robot minus robot actual heading, and then correction equal to error times coefficient of proportional part. And that's literally it. 2 lines, we read the angle, we multiply by coefficient, and we get the correction. Now what is coefficient of proportional part? It's just a number we choose. It controls how aggressively the robot reacts to the error. Small coefficient, robots react gently. Big coefficient, robots react harder. Too big and it overreacts and starts oscillating, and too small and it barely reacts and keeps drifting. And there is no perfect value. You just test it and tune it on your own robot. Let's wrap everything in a function. It takes 3 parameters. Speed is how fast your robot drives. Deck degrees is how far it should travel in moderate degrees, and target heading is the angle we want to stay on. Usually it's at 0, straight ahead. And then this part should be set up before the loop. There is my coefficient of proportional part, and then both motors resets to 0 so we can track the distance, and the gyro resets to 0 so our starting direction becomes the reference point. And this is our loop condition. We take both motors' angles and get the absolute values and add them together and divide it by 2. That's the average distance traveled by both motors. The loop keep running until the average reaches our target distance degrees. Error equal to target heading minus hub emo heading, and then correction equal to coefficient times error, and we apply correction to the speed of our motors, and that's it. And we can use our function, and there is our speed, there is our degrees, and this is our target heading. And let's see it on action. The P controller works, but it has one problem: it overshoots. The robot corrects, goes past 0, swings back, goes past again, it escalates. The D term fixes exactly that. Derivative equal error minus last error, and this is simply the difference between the current error and the error from the previous loop. It tells us is the error getting bigger or smaller and how fast. If the robot is drifting more and more, the derivative is positive and it adds to the correction and we push harder. If the robot is already coming back towards 0, the derivative is negative and it reduces the correction. We slow down the push before we overshoot. That's exactly what kills the oscillation. The robot doesn't just react to where it is, it also reacts to where it's going. And correction equal that equation, and this is a simple formula of the PID controller. And at the end of every loop, we save the current error as last error. So next loop, we can calculate the derivative again. And the KD controls how much weight we give to that rate of change. Too small, still oscillates, and too big, robot becomes sluggish and slow to react. And again, the coefficients are dependent on your robot. As you can see, this is our code. We added only 3 lines. This is a derivative equal error minus last error, and then correction equal to proportional plus derivative gain. And then in the end of the loop, we adding last error equal to the error, so it can calculate the derivative again in the beginning of the next loop. And this is it. And the result, this is our movement of robot, and you can see that it aligning very fast, and that's why the proportional and derivative controller is better than only proportional controller. Now the last term, integral. PD works great, but there's one situation I struggle with. If the robot has a small constant drift that never fully goes away, maybe one motor is slightly weaker, maybe the surface is uneven, the error stays small but never reaches zero. Proportional and differentials see a tiny error and make a tiny correction, but it's never enough to fully fix it. So that's where the integral comes in. Integral equal integral plus error, and with this equation, every single loop we add the current error to the integral. So even if the error is tiny, it keeps accumulating over time. The lower the drift stays, the bigger the integral gets, and the bigger the correction becomes. It basically has memory. It remembers all the past errors and eventually forces the robot back to zero. Correction equal, and with this equation we have 3 parts in the correction. P reacts to now, D reacts to how fast it's changing, and I reacts to the history shortly. And the coefficients of the integral controls how much weight we give to that accumulated error. Keep it very small, and if Ki is too big, the integral grows too fast and the robot will oscillate badly. Now we have the full PID, and let's walk through it. These are our coefficients, Kp, Kd, and Ki, and then this is our full correction formula. This is a proportional part, this is the derivative part, and this is integral part. And that's it, and let's see it on action.